Hi, I'm back. It is Thursday, April 2nd's class. I was gonna do an April Fool's joke with people, but with all you guys, but the only thing all the things I thought of were kind of cruel, so I didn't do them. Best to not do that if it's not going to be received well. So you missed out on April Fool's Day with me. Announcements. So a couple of announcements. Again, next week is spring break, so there won't be any videos coming your way on Tuesday or Thursday, or the day before Tuesday and the day before Thursday. In terms of what's coming up though, we're going to finish chapter 5 today, and that means that test on chapters 4 and 5 is going to be the week after spring break. It won't be on Tuesday, it will be on Thursday. And you can expect to get an email from me probably over spring break, reminding you of the rules and everything that's going to apply in terms of taking that test on Thursday. I'm trying not to change it from the last time. So it will still be a paper test that you'll print out and you will take just like you would in class. But I will send you the rules and regulations and make sure everybody understands that they're to be opening only their email and printing out their test, because yes, your tests are different. They have been ever since the beginning of the semester. So you need to be doing your test and your test only. Let's see, in terms of any other announcements, the only other thing I did want to comment on is the reminder of late submissions. So if I give you an extra credit or a quiz that's due, the word deadline means that's the absolute latest that you can turn it in without losing points. That means that if I give you a deadline of the beginning of class start time, that means your deadline is when class starts for you. So if your class starts at 1:45 p.m., you can't submit it any later than 1:45 p.m. without losing points. And remember that email I sent you about how I was going to get nasty about that, which was, I think, every minute late was 5 points lost. So that means if you submitted your quiz more than 2 minutes late, you just lost all 10 points anyway. So keep that in mind. Things need to be submitted on time, not late. If they're late, you're going to get penalized. In terms of extra credit, if it's late, I'm not even going to look at it. Because again, you need to be keeping on top of things. One of the issues with going online to online classes is that you need to now really organize yourself. You need to still be coming and watching the video at normal class time. That would be the best case scenario, and I talked about this before, so that you're keeping on track with things and not getting far behind. You need to get a system of organization to allow you to succeed in your online classes. So we're ready. I'm done with my speeches. We're ready to go ahead and continue with chapter 5. We were working on 5.5, so I drew the picture up that we need to look at visually, and then we'll talk about the rules for solving a rational inequality. So let me go grab a marker here. And clear my throat. So the idea here is we talked about solving the polynomial inequalities. It really wasn't any different than solving a quadratic inequality, where we go and get critical values and we do test points. The same thing is going to happen with the rational inequalities, but let's take a look at this visual and then we'll see if there's any other issues that we need to think about when we solve rational inequalities. So this is very definitely a rational inequality graph, because I can see the vertical asymptotes and the horizontal asymptotes. I'm being asked, where is this function greater than 0, and then where is it strictly less than 0? So in terms of greater than 0, where is the y value bigger than 0? Well, on this graph, I can see that the y value is bigger than 0 would be this piece right here, and this whole piece right here. which means if I write that with interval notation from left to right, so over x values, I'm starting at an x value of 0, not including it, because again, I want it to be strictly bigger than 0, so I don't want the x-intercept. And then all the way until I get to an x value of 2, where I have an issue, so I can't include it because that's a vertical asymptote. And then over here, I start at 2 and not including it, so union 2 with a parenthesis, and then I go all the way to infinity for x values. So I'm already noticing not only are the intercepts issues, just like they were with the polynomial and quadratic inequalities. In fact, those intercepts, the x-intercepts were the guys that were my critical values, but I also am now having an issue with the vertical asymptote x values, which is basically the domain restrictions. So I'll keep that in mind. And then for where are the y values less than 0? Well, I can see that my y values are less than 0 on this graph. Let's see, this whole piece has y values that are less than 0. And this piece right here has y values that are less than 0. So writing that in interval notation from left to right over x values, I've got an x value here of negative infinity until I get to an x value of negative 2 where I can't quite include it. So I've got parenthesis negative infinity to negative 2. Don't include the negative 2 because again the x value doesn't quite get to negative 2. And then I have this piece right here which is an x value of negative 2 but not quite negative 2. So union parenthesis negative 2 all the way to an x value of 0, which again I can't include because strictly speaking I want y less than 0, so I don't want that x-intercept value right there. So I've got these two sections for where y is less than 0. And again, you can see if you put these together, you'll more or less get the entire set of real numbers except for, before it was just the x-intercepts, but now not only am I accepting any of the x-intercepts, but I'm also accepting the vertical asymptote x values. So again, I can see that for solving a rational inequality without a picture, not only do I have to look at the critical values being the x-intercepts, which we looked at before, but I also have to look at the vertical asymptote x values, so in other words, the domain restrictions being critical values as well. And that's actually the extra piece that we have to do when we solve rational inequalities. So when we go look at the steps that I wrote down for solving a rational inequality algebraically, it says that we want to pretend that it's an equation solved, so same step as before. Those values are going to be the critical values, and again, those were the zeros or the x-intercepts that we'll use to split the number line into intervals. But also included in the critical values of a rational inequality are any values for x at which the original rational expression is undefined. In other words, domain restrictions, which is how we come up with vertical asymptotes as well. So one extra thing we need to consider for critical values for rational inequalities is, are there any domain restrictions, because they will also be critical values. Then we'll use the same thing, we'll use test points plugged in the original inequality to determine which intervals are part of the solution based on what we decide our critical values are. So almost the same process, except for one extra thing I need to think about, which is domain restrictions. So if we take a look at these last two examples, number 3 and number 4, number 3, again, the directions are solve. This is what it says. So I notice it is an inequality and it is a rational inequality. So in terms of solving this, I'm going to pretend it's an equation and get the critical values. So critical values come from pretending that this says x plus 2 over x minus 4 equals 1 and solve that. So to solve this, it's a fractional equation now, or a rational equation now, so I'm going to clear fractions. So I'm going to multiply both sides by the LCD, which is x minus 4. So I'll take this side times x minus 4, this side times x minus 4. This cancels, which was the whole point. So I just have x plus 2 on the left side. The right side, nothing cancels, I multiply, and I get x minus 4. So now it's not a rational equation anymore, it's just actually a linear equation, it looks like. And that means I'll get the x's on one side, the constant on the other side. But what happens when I try to get the x's on one side is that they go away, right? So I'll just do one step here. I subtract those x's, and I end up with this statement, 2 equals negative 4. If you did it all in one shot, maybe you put the x's on the left, you put the constant on the right, you would have gotten 0 equals negative 6. No matter how you look at it, the fact is that the variable dropped out, and you're left with a statement that is very false. When that happens, if the variable drops out and you have a false statement between the numbers, that means there is no solution. So there is no solution here. So this gives no CVs here. So no CVs here, because we didn't get any solution. So now you're thinking, oh, there's no critical values. So I remember we did one like that with the parabola, with the quadratic inequality. No solution, we drew the number line because there were no critical values. We said we could pick any number on the number line, plug it in the original, it's either going to work or not, and we'll know it's either the empty set for the final answer or it's all real numbers. But we're not done here yet. The fact is that there's no critical values coming from this, but where else do we get critical values from rational inequalities? We also get critical values from domain restrictions. So critical values come from setting it as an equation, but also come from domain restrictions. So are there any domain restrictions in this problem? And you're going to tell me, yeah, there sure are. What value can x never be? 4, right? X minus 4 can't equal 0, so x can't equal 4. So there's a domain restriction, so the critical value here is x equals 4. So even though there's no critical values here, there is actually a critical value in this problem, and it happens to be the value 4. So that means I have one critical value. There it is, 4. So I have 2 spots that I need to test. So I'm going to test a value smaller than 4 and a value bigger than 4, and I'll see what kind of answers I get. So in terms of a test point, something smaller than 4, I'm going to grab, you could grab 3 or 1 or 0 is so easy to put in, I'm going to grab 0. So I've got 0 plus 2 over 0 minus 4. Is that greater than or equal to 1? Well, that gives me negative 1/2. Is negative 1/2 greater than or equal to 1? No way. So that guy didn't work. So now I'll pick something bigger than 4, so I think I'll grab 5. So test point at 5. So I have 5 plus 2 over 5 minus 4. Is that greater than or equal to 1? This gives me 7 over 1, so 7. Greater than or equal to 1, that certainly is true. So that means my solution to this problem is in interval notation. So hold on just a second there. Giving away the deal here. So interval notation is from here to infinity, and this says there's an equal sign there, right? And so if it's greater than or equal to, that means you're going to include any of the endpoints. And so you write down 4 with a bracket and you go to infinity, and that's because of this. But then, now you need to be very careful that the fact is that this endpoint, which was 4, was what? It was a domain restriction. Since it's a domain restriction, you still can't include it. Even though this is saying include endpoints, this is a domain restriction, so it means you really can't include it regardless, and so I'm going to put a parenthesis on it because this was a domain restriction and it cannot be included. So my answer for this is 4 to infinity, not including the 4. So be careful with that. I actually, in the steps number 3, you'll notice at the very last sentence there is be careful not to include any values of x that are not in the domain. And the last one here is number 4. same direction, solve. So when I look to see what I need to solve, I see that it's an inequality, and I see that it's rational. So I'm going to go get my critical values. So to get those critical values, I'm going to pretend that it is an equation. So x minus 4 over 2x plus 4 is equal to 1. And then I'm going to remember to also do any domain restrictions. I've got to look at both things. So first let's solve this. I have to clear fractions because it's not a rational equation. So I'll multiply both sides by 2x plus 4. I didn't give myself enough room. So the 2x plus 4's cancel on that side. I get x minus 4 equals 1 times 2x plus 4. Nothing cancels. I get 2x plus 4. So this is not going to be something where I get no solution. So I can see if I get all the x on the right side, so I'll subtract x, I'll subtract 4. I'll get negative 8 equals x. So there's one critical value right there. And now critical values also come from domain restrictions, and there's probably a restriction here that 2x plus 4 can't equal 0. So I'll subtract 4, I'll get 2x can't equal negative 4, I'll divide by 2, I'll get x can't equal negative 2. So critical values, I have 2 of them. My critical values are x equals negative 8 and also x equals negative 2. So I'll just say this for my critical values. So now I'm ready to go put those on a number line and do some test points. So I've got a negative 8, that comes first, and then a negative 2, that comes next. So I have 3 test points that I need to do to see what's going on. So I'll take a test point smaller than negative 8, so maybe I'll grab negative 9, test point negative 9, plug it into the original, negative 9 minus 4 over 2 times negative 9 plus 4, is that greater than or equal to 1? So where I see that x, I'm putting in a negative 9. This gives me negative 13 over, that's negative 18 plus 4, so that's negative 14. So that's actually what? 13/14, right? So is 13/14 greater than or equal to 1? Not quite, so that's a no. So now I'll do a test point between negative 8 and negative 2, so I think I'll grab negative 3 as something a little smaller to help me out. So negative 3 minus 4 over 2 times negative 3 plus 4, is that greater than or equal to 1? So that gives me negative 7 over, that's negative 6 plus 4, so that's negative 2. Is that greater than or equal to 1? Well, that's 7 halves, and 7 halves is bigger than or equal to 1, so this is true. And now I'll go grab something bigger than negative 2, so I'm going to grab 0 now. So test point at 0. So I put 0 in there, 0 minus 4 over 2 times 0 plus 4. Is that greater than or equal to 1? So that's negative 4 over 4. Is that greater than or equal to 1? Well, that's negative 1, so no way. So that means my only piece that works here, so my interval notation is from negative 8 to negative 2. And this says equals, that means include things. So my first shot at this is I write down bracket, negative 8, comma, negative 2, bracket, because again, it's inclusive of the endpoints. But which one of those was a domain restriction? The negative 2 was, so that means my negative 2 cannot have a bracket on it. It's going to have a parenthesis on it, and that's because of the domain restriction. So just don't forget to look at that. So there's my answer for this guy. So solving rational inequalities without having to graph them, because again, I think you're finding out how time-consuming graphing those things can be. So much nicer if we can just do it algebraically. So that ends section 5.5. We're ready to move on to 5.6. So let me get rid of all this stuff. break and get something, a snack or something to drink while I erase the board. Okay, I'm back now. So 5.6. 5.6 is, the title is Real Zeros of a Polynomial Function. We've already talked about what zeros are. Zeros are where y is equal to 0. In other words, they are the x value of the x-intercept. We've talked about their multiplicity. We've talked about their behavior. We've done a lot of things about the zeros. Now I'm restricting in 5.6, this section is restricting the zeros to real zeros as opposed to imaginary, because we can have both, as we know. And it talks about a couple of theorems. I want to take a peek at each one and show you kind of how they're used. So the thing called the remainder theorem says that if f of x, a function, is divided by x minus c, then if I actually evaluate it at the value of c, I should get the remainder. So I wrote down some comments here to try and impress this upon you, but I'm also going to give you a concrete example. So it says, remember a long time ago when we did that division of polynomials, and in this case, since it's being divided by x plus or minus c, because c could be positive or negative, we use synthetic division on that type. That's linear with a leading coefficient of 1. And we talked a lot about how you could write the answer as opposed to just the quotient plus a remainder over the divisor. And one of the ways that we looked at doing it is, remember, we wrote down that f of x is equal to, if you wanted to check it, whatever you divided by, multiplying with the quotient, and then you add the remainder. And we did that to check our division, and this f of x would be the numerator. So we said the numerator was equal to the divisor times the quotient plus the remainder. It was a nice way to check it. The fact is what this is trying to get you to see is that if my divisor, so this is the numerator, if my divisor is x plus or minus c, the book likes to use x minus c, then this says x minus c times the quotient plus the remainder. I'm going to abbreviate a little bit here. So I wrote that down. But notice what this remainder theorem says, is that f of c will give you the remainder. In other words, if I evaluate this when x is equal to c, the 0, you'll get whatever the remainder is. So here's the deal. So I didn't write this line in, so you're going to write it in underneath the line that I have written in. If I evaluate this at c, what am I telling you to do? Replace x with the number c. What happens here? Everywhere I see an x, I put in a c, right? And everywhere in the quotient, I'm going to put a c in for the x. Notice I don't even know what the quotient is. And if the remainder has an x in it, I'll put a c in there. But it doesn't really matter, because take a look at this first part right here. What is c minus c? 0. What's 0 times anything? 0. So this whole piece is going to go away, and you're going to end up with f of c gives you the remainder. So that's exactly what the remainder theorem is saying. If you evaluate a function at a particular number, the answer that you get will actually be the remainder if you were to divide by the x minus the c. So let me give you a concrete example. So as a concrete example, if I said, let's see if I can read my writing here, x cubed plus 4x squared minus 7, and we divide it by x plus 3. So we can do synthetic division on this, right? What am I synthetically dividing by? Negative 3. Okay. And, oh, there's something missing there. So I've got a 1, and then a 4, and then a 0, and then a negative 7. I bring down the 1, I multiply, I get negative 3, I add, I get 1, I multiply, I get negative 3, I add, I get negative 3, I multiply, I get 9, I add, and I get a remainder of 2. So now I want to challenge you to remember how to write this in this form. So in other words, what this is saying is that f of x, which is the numerator, okay, so the numerator, which is x cubed plus 4x squared minus 7, and we'll call it f of x in a minute, is equal to the divisor. Well, we synthetically divided with negative 3, so that means our divisor is x plus 3. multiplying with the quotient, which is right here. So do you remember how to write this as a quotient? This is the constant, this is the x, this is the x squared. So that would be x squared plus x minus 3, and then plus the remainder. So that's how we actually wrote this way back in chapter R, I think. If I sub this out for f of x, this f of x is like my numerator, then this says f of x is x plus 3 times x squared plus x minus 3 plus 2. So first of all, my first comment is x plus 3 a factor of f of x? Is x plus 3 a factor of this numerator? And you're going to tell me no, because there was a remainder, right? In order to be a factor, the remainder needs to be 0. And that's something that we always like to be able to have as a factor where there is no remainder. So clearly, x plus 3 is not a factor. But on top of that, if I would have just taken this original f of x and evaluated it at -3, so f of -3, I should get the remainder. It should give me 2, because look, you put -3 in there, what happens is this whole first piece turns into 0, because that's 0 times anything is 0, and you just get 2. This is what the remainder theorem is saying. With that in mind, so now check this idea. In other words, if f of x is my x cubed plus 4x squared minus 7, what is f of -3? So I could plug it in there, and when I plug it in there, I should get 2. So let's try it. I have a -3 cubed plus 4, -3 squared minus 7. Well, this gives me -27. That's 9 times 4, so positive 36 minus 7. So there's -34 plus 36. There it is, and that will happen every time. So kind of a nice thing. When the number's easy to plug in, you can kind of see what the remainder is. And of course, our goal is going to be to have a remainder of 0 as we go through this section and the next section. This is showing me that -3 is not a 0. And in fact, x plus 3 does not divide in evenly. It's not a factor. So with that in mind, there's this thing called the factor theorem. And it states, let me go get rid of this. So these two theorems are kind of tied together. They're on related ideas. The factor theorem says that x minus c is a factor of f of x if and only if you take f and evaluate it to c, you get 0. In other words, the remainder needs to be 0 for this to be a factor. And we talked about this way back in chapter R when we were doing synthetic division and long division. So in other words, the remainder needs to be 0. So x minus c is a factor of f of x. It goes in evenly if and only if the remainder is 0, which is what that f of c gives you. This is the remainder right here. So the remainder would have to be 0 for it to be a factor. And then I just commented a few other ideas, or just tying things together again. If c is a 0 of the polynomial, then that means that c comma 0 is on the graph of the polynomial. In other words, zeros are x-intercepts. I can't harp on that enough. And if c is a 0, then x minus c will be the factor that it comes from. So with these two theorems kind of in mind, I have two examples here. The directions say use the remainder theorem to find the remainder when f of x is divided by whatever I've written down, whatever x minus c is. And then on top of that, I ask you if x minus c is a factor. So I'm actually going to show you two ways to look at this. The new way with the remainder theorem and the old way, which is to synthetically divide it. So the question here is, here's f of x. And we're trying to decide if x minus 2 is a factor or not. So not only do we want to figure out the remainder, But as a result of that, we want to decide if it's a factor or not. And of course, for it to be a factor means that the remainder will have to be 0. It has to go in evenly. So the old way to do this was to synthetically divide it. The new way is to think about the remainder theorem, which says that if you take this function and evaluate it at the 0 that this would give you, you'll get the remainder. So in other words, I want to evaluate this function. If I'm trying to see if x minus 2 divides in evenly, I would be plugging in a positive 2, the opposite of this, just the same thing I would be synthetically dividing with. In other words, I'm trying to figure out if the answer is going to be x minus 2 and then the quotient and no remainder, or what would the remainder be. So I'm going to plug in 2 and see what happens and see what my remainder is. So this can be time consuming. 1 and -1, not so hard, but the minute the numbers get bigger and this polynomial function has a lot of powers and a lot going on, sometimes I find the remainder theorem the harder way to look at things. But I'm going to go ahead and do it, and then I'm going to show you using synthetic division how we could make sure as well. So if I plug in f of 2 here, I would have 2 to the 5th plus 6 times 2 to the 4th minus 11 times 2 cubed minus 12 times 2 squared plus 5 times 2 minus 20. Just doing all that, to me, feels like it takes too long, but I'm going to go ahead and do it and use that remainder theorem, and then I'll show you how we can double check things. So let's see, when I go evaluate this, I get 2 to the 5th, which is 32, plus 2 to the 4th is 16, and 6 times 16 is 96, minus 2 cubed is 8, and 8 times 11 is 88, minus 2 squared is 4, so that's minus 48, plus 10, minus 20. Alright, so now what do I have here? Oh, let's see, I've got 128 minus 88, which is 40. That gives me -8, -28, plus 10, negative. So I get -18 there, so check me on your calculator. Make sure that I've done that right in my head. So f of 2 is -18. And what does that mean? That means this guy right here, this is the remainder. Remainder when dividing by x minus 2. In other words, we synthetically divided by 2, so we're plugging a 2 in, and we got -18. So is x minus 2 a factor? X minus 2 is not a factor because my remainder is not 0. Remainder is not 0. So another way of doing it, using this thing called the remainder theorem. Maybe you don't like that. Honestly, I only like it for testing 1 and -1, but let's go look at how we used to do it. If I wanted to know if x minus 2 is a factor of this, I would synthetically divide. So I would synthetically divide with 2, and nothing's missing. So I have a 1, a 6, a -11, a -12, a 5, and a -20. Bring down the 1, 2 times 1 is 2, add, I get 8, 2 times 8 is 16, add, I get 5, 2 times 5 is 10, add, I get a -2, 2 times -2 is -4, add, I get 1, 2 times 1 is 2, add, and I get -18. There's my remainder. I kind of think that's still a little faster, except for maybe 1 and -1. Plugging those in isn't too difficult. So what is this telling me? This is telling me, so let's really write this down. What this is telling me is that f of x is equal to, I synthetically divided with positive 2, so the factor that I was dividing or trying to see if it was a factor or not was x minus 2. This is the quotient right here, which is going to be an x to the 4th, and then an 8x cubed, and then a 5x squared, and then a minus 2x, and then a plus 1, and then the remainder, minus 18. Is it a factor? No, it didn't go in evenly. In other words, if I plug 2 in here, this will all go away and I'll just get negative 18, which is what I got. But ultimately, it's not a factor. And honestly, for our purposes in the next 2 sections, we're looking for factors. So we're looking for a remainder of 0. So the next one, same type of question. We'll do it both ways again. Again, I'm asking, is x minus 2 a factor? So one way, so this one isn't as long, this polynomial function. So I could do the remainder theorem. If I'm dividing by x minus 2, I would be synthetically dividing with a positive 2. So that's the value I'm going to actually put into this function, positive 2. If I don't have a remainder, it would be the 0 of the function when what value is x, when y is 0. So I plug a 2 in there, so let's see, I got 3, 2 to the 4th, minus 6, 2 cubed, minus 5 times 2 plus 10. That 2 to the 4th is 16, 3 times 16 is 48, minus 8 times 6, which is 48, minus 10 plus 10, oh, I can see this. This is 0. So this is the remainder. Remainder when divided by x minus 2, which means that x minus 2 is a factor. So x minus 2 is a factor because the remainder is 0. How did we do this the old way? Is because honestly, even with this remainder theorem, even if I get it that the remainder is 0 and it goes in evenly, I still don't know what the factors are. I know one of the factors is x minus 2, but I don't know the other factor. The only thing that will get me that other factor is synthetic division anyway. So I'm going to go ahead and synthetically divide again with 2 if I'm dividing by x minus 2. In terms of missing pieces, I do have a few. I have a 3 and then a negative 6. I have no x squared, and then my x is negative 5 and my constant is 10. Bring down the 3. 2 times 3 is 6, add, I get 0, 2 times 0 is 0, add, I get 0, 2 times 0 is 0, add, I get negative 5, 2 times negative 5 is negative 10, add, and I get 0. So there it is, remainder is 0, so it is a factor, but now I can also express its factors, and I can actually have a polynomial function partially factored that I might not have known how to do with my normal factoring rules, and that's actually where we're going to with this. So this says that f of x is equal to, I synthetically divided with 2, so that means the factor is x minus 2. And this is the other factor, which is 3x cubed minus 5. And there is no remainder. So look at what happened there. I actually got this thing factored into 2 pieces. They're not both linear yet. This one's linear. This one I would have to maybe try to work on more if I could. And this is something that we wouldn't know how to factor with our normal, well, actually maybe I could have, but with grouping. But sometimes there are problems that you can't factor with normal rules, and you do this idea of synthetic division looking for a remainder of 0 so that you can get it factored, and that's where we're headed. So the next theorem that's in this section is called the rational zeros theorem. And what the rational zeros theorem does, so rational again means anything that can be expressed as a terminating decimal or a repeating decimal. So everything except for irrational numbers or imaginary numbers. So it says that this rational zeros theorem finds possible values of rational zeros. And notice that I said it says nothing about irrational zeros or imaginary zeros. This theorem only finds the possible rational zeros that we can then try to see if they really are zeros of the function. And again, zeros of the function means the x-intercept, which means where is the y value 0? And if you think about all these things we keep writing down, if I want to see where the y value is 0, I will put a 0 here and try and solve this, which means I want to try and factor it, and that's what this is all about. So it says that the polynomial, first of all, has to have integer coefficients, which it's going to have. We'll keep it that way. And it says, oh boy, here we go. If p is a factor of the constant term and q is a factor of the leading coefficient, then plus or minus p over q in lowest terms will describe the possible rational zeros of the polynomial. Wow, okay. So let me erase this. I'll let you look at that again, read through it one more time. So this is a theorem that helps me to find possible rational zeros. And they're talking about factors of the constant term, and they're talking about factors of the leading coefficient. So let me put the very first problem up here. It's all nicely in order. And the directions are find all the possible rational zeros, so using this rational zeros theorem, find all the possible zeros, then use them to factor and or solve, because I have one in here that the directions say solve. And in parentheses I wrote the factors. When you get this factored, they need to all be linear. Every single one needs to be linear, or else it will not at this point be considered factored completely. So they want me to find all the possible zeros, and then they want me to use them to factor, in this case, to factor this polynomial. So my ultimate goal here is to factor this, because if I have it factored, remember when we were graphing the polynomial functions, they were all factored for us so that we could pick out the zeros and their multiplicities. When I'm given a function that's not factored for me, and they want me to graph it, I need to get it factored so that I can then do section 5.2 where everything was already factored, and I can go and try and graph it. I can get end behavior, I can get the zeros and their multiplicity, and the behavior at the zeros, and then I can go pick some y-intercept and some extra ordered pairs to get it filled in. But if I'm given a polynomial function that looks like this, then I have an extra step before I can even do what we did in 5.1 and 5.2. I have to get it factored first so I can see its zeros and their multiplicities. So how do I get this factored? Well, looking at this with our normal way of factoring, there are 4 terms. And so you go, oh, I'll try and group. And when you try and group this, you fail. I can't, if I group these two and these two, I pull an x squared out, I get x plus 8. There isn't even anything I can do with those, and this doesn't say x plus 8. If I try and rearrange, I still get stuck and nothing seems to work. And so then I go, oh no, I can't factor this, so what am I going to do? How am I going to figure out the zeros and stuff? So that idea fails, and so the next idea is if I can come up with possible values to test and see if they were actually zeros, I might be able to get this factored. And that's what this theorem is about, is to come up with the possible zeros, and then we'll go test them and see if they actually are zeros or not. In other words, is the remainder going to be 0? And are they going to be x-intercepts or zeros? So I look at this, and using that theorem, they're talking about factors of the constant term, which is this guy, and factors of the leading coefficient, which would be the coefficient in front of this x cubed, which is a 1. I'm going to list the factors of this guy, and then I'm going to list the factors of this leading coefficient. One of them is p's, the other one is q's. And so if I look at this again, they're saying that the p's are the factors of the constant term, and then the q's are the factors of the leading coefficient. And then I write plus or minus p over q, all in lowest terms, as possible rational zeros of the polynomial. So here I go. All possible factors of 20. Don't have a sign for now because I'm going to put a plus or minus in front of everything anyway. So factors of 20, start counting. Don't leave any out. So 1 goes into 20 20 times. I like to put them in order from smallest to largest, so I'm going to leave a little bit of space. 2 goes into 20 10 times. Didn't leave myself enough space. 3 doesn't go in evenly. 4 goes in 5 times. Now I'm at 5 and I already have it. That way you know you're done. So just start counting 1, 2, 3, 4 and keep until you get them all. So there's all the factors of 20. The leading coefficient here is 1. The only factor of 1 is 1. These are my P's. These are my Q's. I always have to think about minding my P's and Q's when I say that. And I don't even know what that stood for, but I know my mom used to always say that. That gives you an idea how old I am. So the possible, it might not work, but possible rational zeros, I'm going to list them. Plus or minus P over Q in lowest terms. So this over this. Luckily there's only one term here. So I just have to put this over this, and then the 2 over that, and then the 4 over that, etc., and I'll be done. And put a plus or minus in front of each one. I'm going to put a plus or minus once and say it goes for all of them because it just makes it easier to write. P over Q. So 1 over 1 simplified is 1. 2 over 1 simplified is 2. 4 over 1 simplified is 4. 5 over 1 simplified is 5. 10 over 1 simplified is 10. 20 over 1 simplified is 20. And I'm all done with that one. There's my possible rational zeros. Plus or minus 1, 2, 4, 5, 10, or 20. So there are actually 1, 2, 3, 4, 5, 6, 12 possible rational zeros. Because either one of these could be positive or negative. So what are we going to do with it? Because notice the ultimate directions are find all the possible rational zeros, but now get this thing factored in linear factors. So how do I factor this? I have to figure out which one of these would be good choices to give me a remainder of 0. So one thing I can do is the remainder theorem, at least for the 1 or the negative 1 maybe, to help me out. But then otherwise, I'm just going to do synthetic division because it's quicker and it gives me the other factor, which I need to have anyway. So I could test real quickly 1 by plugging 1 in there and seeing if I get 0. So if I put 1 in there, I'll have 1 plus 8, which is 9, plus 11, which is 20. I think 1's going to work. And so I do take a quick check, but you still need to do the synthetic division because I need the other factor. I need the answer, the quotient. So I think 1 will work. If 1 didn't look like it was going to work, then I would try negative 1 next. If that doesn't look like it would work, then I'll go to 2. And at that point, I stop plugging them in. I just start doing the synthetic division. Sometimes this can take a long time. When I learned this, oh gosh, eons ago, my teacher liked the idea of giving us nasty things that would work, like 2/3 and stuff, and we'd be synthetically dividing with it. I'm not going to be quite that bad. So here we go. I think 1 works, so I'm going to go try it. So I synthetically divide with 1. Everything is in order, nothing's missing. So 1, 8, 11, negative 20. Bring down the 1. 1 times 1 is 1. 8 plus 1 is 9. 1 times 9 is 9. 9 plus 11 is 20. 1 times 20 is 20. There's my remainder of 0. So now, what do I know so far? So write down the factor that you have discovered. So in other words, f of x is equal to, I synthetically divided by 1, which means what I really divided by was an x minus 1. It's the opposite of this. So my 0, this is my 0 right here. This is the 0, which means the factor would be x minus 1. And this is the quotient, which is x squared plus 9x plus 20. No remainder. So I already have my original function slightly factored just by testing the rational zeros. And I lucked out, and the very first one worked nicely. It gave me a remainder of 0. So I've got it partially factored now, which I couldn't do with my normal ideas of factoring. So now the question is, this is linear, but this isn't, not yet. So the next question is what do I do with this? This is actually called the depressed factor that we haven't finished factoring yet. I don't know if it's sad or why they call it a depressed factor, but anyway, we have 2 choices here. If I can see how to factor it with traditional methods, then I will. If I can't, then I will look at my possible rational zeros and think about dividing them synthetically into this depressed factor and see if I get a remainder of 0. But I think this one we can handle with our normal factoring. This is quadratic. It's 3 terms. So I think the easy big X will work on this if I can get it factored that way. So multiply to 20, add to 9, that's going to be a 4 and a 5. So here we have f of x is equal to x minus 1. This factors into x plus 4, x plus 5. So now it is completely factored in linear factors, which is what they wanted me to do. I want to tie a few pieces together here. I know it didn't ask for anything else, but here's the deal. Here's that polynomial function that we were trying to graph back in 5.1 and 5.2. Can you now proceed? I can figure out n behavior. I had the original one, so I can figure out n behavior from it, or I can figure it out here. I can now figure out all the zeros and their multiplicity. So I'm going to actually have you tell me what they are. So tell me the zeros and their multiplicity. So the 0 here would be 1 multiplicity 1, right? 0 here would be negative 4 multiplicity 1. The 0 here would be negative 5 multiplicity 1. So now I know the behavior at the zeros from that information, and I can get on my way to graphing this thing, when before I didn't even know where to start because it wasn't factored for me. And notice the possible rational zeros. Here's the actual, these are possible. Here's the actual ones. 1, which was in my list of possibles. Negative 4, which was in my list of possibles. And negative 5, which was in my list of possibles. And they should always be in that list of possibles if I'm finding them as actual ones. So just kind of trying to tie the ideas together. So the second one, same question. They want me to try and factor this. And they want me to find all the possible rational zeros and then use those to try and get it factored. So, possible zeros, I need to factor the constant and the leading coefficient and list all of its factors. So factors of 30 are 1 and 30, 2 and 15, 3 and 10. I still didn't leave myself enough room. 4 doesn't go into 30, 5 and 6, 6 and 5, I've listed that already, I'm done. So there's all the factors of 30. And this is now a leading coefficient of 3, so factors of 3 are 1 and 3. These are my P's, these are my Q's. So my possible rational zeros are plus or minus, so plus or minus P over Q simplified. So now you have a little more work to do. Stay organized. So either do this one over this one and then do it over this, or do all of these over the 1, then come back and do all of these over the 3. That's how I would recommend doing it so that you don't have repeats. So I'm going to do all of these over the first Q, and then I'll do all of these again over the second Q. And if there was a third Q, I would do all of those over the third factor for Q. So here we go. Plus or minus 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 5 over 1 is 5, 6 over 1 is 6, 10 over 1 is 10, 15 over 1 is 15, and 30 over 1 is 30. So there's the first round. Now I'm going to go do it again and put them over 3. So 1 over 3 is 1/3, and that is simplified. So I'm gonna go down here and continue this since I'm out of space. 2 over 3 is 2/3 simplified. 3 over 3, when I simplify it, is 1, and I already have it listed. Don't list it again. 5 over 3 simplified is 5/3. 6 over 3 simplified is 2, and I already have 2. Don't list it again. 10 over 3 is 10/3. 15 over 3 simplified is 5, and I already have 5. Don't list it again. 30 over 3 is 10, and I already have 10. Don't list it again. So my possible rational zeros, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got 24 of them, plus or minus, so 12, but they can be both sides. I've got a lot of them, and here's what I was talking about. The teacher I had when I took this a long time ago. I think it was like 10th grade AP, I don't know. I was one of those, yes. She would make sure that it was one of these guys. None of these would work. We'd sit there and do the synthetic division on all of them, and none of them would work. It'd be one of these guys. So mean. So here we go. I'm going to start trying to find the zero so that I can begin to get this thing factored. So in terms of what I want to choose, I always start over here. And for the 1, I would plug it in if I can do it quickly. If I can't, then it's not worth it and just do synthetic division. But I can kind of see the 1 because 1, positive 1, none of these signs will change. So I've got a 9 and it's 2 negatives. So I don't think 1's going to work. So maybe negative 1 would have worked. So this takes a little more work, but it's not too bad. If I put a negative 1 in there, that'll be a negative 3. This will stay positive. This will turn into a positive, and this will stay negative. The negatives are still way too big. And so I kind of do a quick thing with the 1 and the negative 1, to be honest with you, with the remainder theorem. And now I'm just going to go ahead and start synthetically dividing, but I'm going to skip 1 and negative 1 because I don't think they work. So I'm going to go to 2 next. So I'm going to synthetically divide with 2. And let's see what I've got here. I've got a 3 and then a 6 and then a negative 15 and then a negative 30. So they're in order, cube squared. And I'm going to go try it. So I bring down a 3. 2 times 3 is 6. This is me 12. 2 times 12 is 24. I add and I get 9. This isn't going to work. Okay, so if you can see the writing on the wall, you can stop and move on. So either start a new row, or I'm going to leave this and just erase these. And instead of synthetically dividing with, bring that down. Instead of synthetically dividing with 2, now I'm going to try the negative 2 and see if it works better. And then if it doesn't work, I'll move on to the 3 and then the negative 3. So I bring down the 3, negative 2 times 3 is negative 6, I get 0, negative 2 times 0 is 0. I add, I get negative 15, I think this is going to work. Negative 2 times negative 15 is positive 30. I add and I get 0. There it is. So now stop and write down what you have so far in terms of the factoring. So this says f of x is equal to, if I synthetically divide it with negative 2, the factor is x plus 2. This is the quotient, so the depressed factor would be 3x squared minus 15. So this is what I have so far. And I suspect I maybe would have been able to get that with grouping, but we're trying to practice this new idea because when normal factoring fails, then I have to have a better way to do it, or another way to do it. So this is linear. This is not yet. So the question is can I factor this to get it to be linear with my normal factoring methods? Do I need to take it and synthetically divide with it, with my depressed factor? Well, I'm going to try to play with this a little bit. I can certainly see a GCF there. So the fact is that I have my x plus 2. If I pull a 3 out of there, I'm going to put the 3 in front of everything instead of smushed in between. And this will leave me this factor with an x squared minus a 5, right? In other words, I'm pulling a 3 out of here, getting x squared minus 5, and I'm just pulling the 3 out in front of everything to make it look nicer. It's still not linear though. Okay, so I got the GCF out. So now the question is can I keep factoring that? Well, our rules say difference of 2 squares, and then you tell me, oh, but that's not a perfect square, so I can't factor it any further. Well, I'm here to argue with that now. So the fact is even if it's not a perfect square, I can still factor it further. And here's how. So think about this for a minute. If I were asking you to find the zeros for me, in other words, when y is 0, what would my answers be? You'd tell me one of the zeros is negative 2, which we kind of found right there. And how would you find the zeros here? If you can't factor it, then you would use other methods of solving the quadratic, right? And so if we were finding zeros, we would say that x equals negative 2 is 1, and then we would say x squared minus 5 equals 0 because we can't factor it, we would solve it another way, and we would go like this, most likely. We'd use the square root property. X squared equals 5, so x is equal to plus or minus the square root of 5. Well, guess what? That's really just saying that we could have factored that. The fact is if we factor that difference of two squares, even if that's not a square, you take the square root of that and you take the square root of that and you add them and you subtract them, which is exactly what we're finding our zeros are anyway. So my conclusion here is that you can factor the difference of squares even when you don't have perfect squares. You can either do it by figuring out what we just did, which is what the zeros are, or you can just think a little bit outside of the box and take the square root of 5, even though it's not a perfect square, and just write it down as the square root of 5. So my final conclusion here for factoring this is f of x is equal to x plus 2, x plus the square root of 5, x minus the square root of 5. And now I have it factored in linear factors, which is what they asked me to do. And again, to tie it together, and you can either do this by thinking outside the box or do it the way we did it before, trying to think about the zeros. If they were to ask me what the actual zeros are, you would tell me -2 is a 0 of multiplicity 1. You would tell me negative square root of 5 is a 0 multiplicity 1. And you would tell me square root of 5 is a 0 multiplicity 1, which is exactly what we found right here. Are these guys part of my possibles? Well, -2 certainly is, but these guys aren't, are they? But remember what we said, this possible rational zeros theorem only gets rational zeros, possible rational zeros. These are not rational, these are irrational. We had to go find them another way. But we were able to break this down enough to have another way that we know to figure those out. So let's see, we're ready for number 3. I keep forgetting you can pause it and get everything written down so I can go ahead and erase it. So number 3 also wants me to factor. And I know the directions said more than just factor, but even if they had just said to factor into linear factors, this is one where I wouldn't know where to start with our normal factoring methods. There's 1, 2, 3, 4, 5 terms. I can try and do some sort of interesting grouping, but I would have to group 3 terms maybe in 2 terms and play with that. It's probably easier to go and try and find rational zeros, synthetically divide and see if I can actually find a way to factor this a little bit to get it broken down to a depressed factor that I can then factor with my normal methods. So I'm going to go look for possible rational zeros. So I need factors of 8. So 1 and 8, and 2 and 4. 3 doesn't go into it. 4, and I'm done. And factors of the leading coefficient. Oh, this is nice. That's just a 1. So these are my P's. These are my Q's. So possible rational zeros are plus or minus P over Q simplified. So nicely enough, the Q is just 1, so I'm only going to have to do one round of this over this with a plus or minus in front of it. So 1 over 1 is 1, 2 over 1 is 2 simplified, 4 over 1 is 4 simplified, 8 over 1 is 8 simplified. So there are 8 possible rational zeros. So I need to go find at least one of them so I can start to get this guy factored. If I look at 1, just quickly with the remainder theorem, I plug 1 in there. That's 1 minus 1, so that's 0. That's a negative 6 plus 4 plus, that's not going to work. Too much on the positive side. So maybe negative 1 would work. So quickly, don't take too long. If it takes too long, just do the synthetic division. Negative 1, this would stay 1. This would be a negative, so this would turn into a positive 1. This would stay negative. This would be negative, and this would be positive. Oh, that works. So I think negative 1. So I'm going to go try negative 1 on this guy as my first try here and see what happens. Hopefully I'll get a remainder of 0. So, and nothing's missing. So I've got 1, negative 6, 4, and 8. And I bring down the 1. Multiply, I get negative 1. Add, I get negative 2. Multiply, I get positive 2. Add, I get negative 4. Multiply, I get 4. Add, I get 8. Multiply, I get negative 8. Add, there it is, 0. So now, write down where you are. That says that my f of x is equal to, if negative 1 is the 0, then the factor it's coming from is x plus 1. This is the depressed factor or the quotient. So this is going to be x cubed minus 2x squared minus 4x plus 8, no remainder. So I have this thing partially factored already. I've got this factor out. This is not linear yet. So now I have choices. There are 4 terms here now, so maybe I can do grouping and figure it out. And I think I probably can take an x squared out of there. I get x minus 2. Take a negative 4 out of there, and I get an x minus 2. So grouping would work on this. So I'm actually going to do this both ways. Because what if you can't see how grouping would work on this? Then what would you do? Because I want these in linear factors. So let me do it with grouping first, and then I'll do it the other, well, I'm trying to think about which way I'd rather do it first. Let's pretend that we didn't see grouping here. And we said, now what do I do? Well, now what you're going to do is take the depressed factor and synthetically divide with any one of these. Now the fact is 1 didn't work, and if 1 doesn't work on the original, it's not going to work on the depressed one either. Negative 1 did work, so negative 1 might work again on the depressed one, or otherwise I'll start going to 2 and negative 2. So in other words, you take the depressed factor and continue with it. So I would take this guy, which is, and I've got to think about what I want to synthetically divide by. I would have a 1, a negative 2, a negative 4, and an 8. In other words, these guys right here. And I'm not going to synthetically divide with 1 because I already ruled it out. Negative 1 might work again. Sometimes that happens. It would be their multiplicity too. But when I look at this and I put a negative 1 in there, that would be negative 1. That would stay negative 2. But that would change to positive. Way too much positiveness. So I'm thinking negative 1 is not going to work again. So I'm going to resort to 2 and see what happens when I do 2. So let's see. And again, this is the depressed factor. Don't start at the beginning again. You're not going to get anywhere. We're trying to factor this piece now. So I bring down the 1, I multiply by 2, I get 0, 2 times 0 is 0, I add, I get negative 4, 2 times negative 4 is negative 8, oh look at that was nice. I get a remainder of 0. So what does this now say? This now says that f of x is equal to, so don't lose that factor that you already figured out, x plus 1. You're now factoring this depressed factor, and what did you find out about it? You found out that synthetically dividing with 2 goes in evenly, so the factor would be x minus 2. And the other piece, the quotient, is x squared minus 4. No remainder. So in other words, here was my original. So far I had x plus 1, and then I had x cubed minus 2x squared minus 4x plus 8. And this piece right here broke down into x minus 2x squared minus 4. So now what can I do? Well, this I should be able to do without synthetic division. This applies actually to my nice, easy factoring difference of squares. So f of x is equal to x plus 1, x minus 2. What does this turn into? X plus 2, x minus 2. So I see some similarities there, so let me write this one more time, or f of x is equal to, I've got an x plus a 1, I've got an x plus a 2, and I actually have an x minus 2 what? Squared, right? Because that'll help me in terms of zeros and their multiplicity. So I got this thing all factored. I used the depressed factor to keep going here because sometimes you have to if you can't figure out how to factor the depressed factor on your own with normal factoring rules. And we'll look at that in a second. I promised I would. So, but let me tie this together now. So what are my actual zeros? So actual zeros are -1 multiplicity 1, -2 multiplicity 1, and 2 multiplicity 2, which makes it so that I can get this thing graphed if I want to. So now, so this is my final answer here. You see this guy right here, x cubed minus 2x squared minus 4x plus 8. Suppose instead of trying to do synthetic division on it more, we decided that we knew how to factor it. That's fine. You do grouping, right? So you take out an x squared, you get x minus 2. You take out a -4, you get x minus 2. Remember, these guys have to agree. So one of the factors is x minus 2, and the other one is x squared minus 4. That's always quicker if you can figure out how to do it. So see that? There it is right there. So either way is fine on that depressed factor. If you can figure out a way to factor it, go for it. If you can't, then you need to do synthetic division on it and continue. So we've got one more here, number 4. And number 4, the directions say solve this time instead of factor. But in order to solve it, I think we need to factor it. So let's take a look at that one. So they want me to solve this mess. And this is higher degree than a quadratic, but we said even if it's higher degrees, the idea of how to solve this is to try and factor it because it's equal to 0, so you can do that extension of the 0 factor property. But how the heck do I factor that? 1, 2, 3, 4, 5 terms, so either try and get creative with grouping, or I think about trying to find possible rational zeros and then finding which ones are the real rational zeros and get it all factored and then solve it. So I'm going to go that route. So with that in mind, I need factors of 9. So 1 and 9. 2 doesn't go in. 3 does. So 3 and 3. I don't need to list it twice. So 1, 3, and 9. Factors of 1 are 1. These are my P's. These are my Q's. So possible rational zeros are plus or minus P over Q. So 1 over 1 is 1, 3 over 1 is 3, 9 over 1 is 9. So there are 6 of them, plus or minus 1, 3, and 9. So I'm going to go and I'm going to go try and see which one I want to synthetically divide with and hope for a 0 for my remainder. If I look at, again, I do just plug in 1 and -1 usually because sometimes it's quicker. If I plug 1 in there, that's 1 minus 2, which is -1, plus 10 is 9, 18. I think 1's going to work. So I'm going to go ahead and do synthetic division with 1 and hope that I did that correctly. So I've got everything's in order here. 1, -2, 10, -18, and 9. Bring down to 1. 1 times 1 is 1. Add, I get -1. 1 times -1 is -1. Add, I get 9. 1 times 9 is 9. Add, I get -9. 1 times -9 is -9, add, there's my 0. So what do I have so far in terms of factors of this left side? If 1 is a 0, then the factor it comes from is x minus 1, and here's the depressed factor, which is going to be x cubed minus x squared plus 9x minus 9, and that all equals 0. Remember, there's an equation here as opposed to an f of x. So now I need to take this thing and see if I can factor further. This is linear, but this sure isn't. So I can either take this depressed factor, write it down and synthetically divide with it, or if you can see a way to get this factored without having to do more synthetic division, then go for it. And I think I can do grouping on this one. So let me just look at this piece and this piece. If I take out an x squared, I'll have x minus 1. And here if I take out a 9, a positive 9, I'll have x minus 1. That's good. So that means from this I get a factor of x minus 1, and then a factor of x squared plus 9. And I still have this guy, don't lose sight of him. So I have x minus 1, x minus 1, x squared plus 9 equals 0. So that's what I now have in terms of this guy being factored. This is linear, this is linear, this is not. We're trying to solve this, so we could go back to traditional ways. This is quadratic, so there are other ways to solve this, clearly. Or you can think about, let's see, oh, but this is the sum of squares, okay? And what we say, sum of squares is prime. Again, I could think outside of the box, but I'm going to go with that for a second and just show you what happens here. So this basically says that x is equal to 1 or x is equal to 1 again. So that 0 of 1 is multiplicity 2, right? But we're trying to solve this. So, or x squared plus 9 is equal to 0, and I need to solve that. So what happens when I solve that? I subtract 9 because I can use square root property. So I get x squared equals negative 9. I do the square root, plus or minus the square root. And what do I get here? X equals plus or minus what? It's imaginary, isn't it? 3i. So what is that telling me? That's telling me that the zeros are 1 multiplicity 2. There's a 0 of positive 3i, and there's a 0 of negative 3i. So let me write that down. I know they only asked me to solve it, and here's my answer right there. X equals 1, or x equals 3i, or x equals negative 3i. But let me again tie this together. This is saying that my zeros are 1 multiplicity 2, and then I have a 0 of 3i multiplicity 1, and negative 3i multiplicity 1. Notice imaginary always come in pairs of conjugates. We talked about that with quadratic equations. It's the same for every equation. They come in conjugate pairs, which means that, so now I want you to think about the factoring of this. I know it's equal to 0 and we were trying to solve it, but just humor me a little bit. If 1 is multiplicity 2, that means my factor was x minus 1 squared, right? If 3i is a factor, that means that if 3i is a 0, that means my factor would be x minus 3i, just there once. And if negative 3i is 0, that means x plus 3i would be my factor. So this is actually what it looks like factored. X minus 1 times x minus 1, so I wrote it x minus 1 squared. X squared plus 9 actually does factor. It factors linearly into x plus 3i, x minus 3i. And so this is actually everything factored linearly, so linear factored. So just a comment because it's a nice segue into the next section. So we're ready for the last section here, 5.7. And oh, look at that handout. It only has one side. Shocking. So 5.7, I would tell you not to let me forget, but before I end, I need to write up 2 answers to the homework in 5.7 in terms of how I want them written, but hopefully I'll remember to do that. So 5.7 is about complex zeros of a polynomial function. In other words, imaginary zeros of a polynomial function. And we just had one that had some imaginary zeros in it. So we kind of explored the idea already. We're going to explore it in a little more detail in this section. There's one important theorem in this section, and it's called the conjugate pairs theorem, which I just reminded you of. It says that if you have a polynomial that has real coefficients, if a plus bi is a 0, then so is its conjugate a minus bi. That will always be the case, not just for quadratics, for any polynomial equation where it has real coefficients, which partially makes it polynomial. you will always have conjugate pairs if they are imaginary, not the real numbers, just imaginary numbers. So in other words, if 2i is a 0, then so is negative 2i. If 3 minus 4i is a 0, then so is 3 plus 4i. They come as conjugate pairs, just like they did with quadratic equations. They come that way with all polynomial equations. So a very powerful theorem. We're ready to look at these examples to see what it can do for us. So this example number 1 says find the other zeros. So they tell me that, so they don't even tell me the equation. They just tell me that it's degree 6, which means it has how many zeros? How many, at most, how many distinct zeros can it have? If it's degree 6, it can have 6 distinct zeros, right? It might not have all 6 because some of them might be multiplicity, something other than 1. But at most it can have 6 zeros, each one multiplicity 1. And what they've told me so far is that there's a 0 of I, there's a 0 of 3 minus 2i, and there's a 0 of negative 2 plus I. The fact that they didn't give me multiplicities means that they are multiplicity 1. I know we always write it out, but the book tends not to. So how many zeros has it given me? 3 distinct zeros, but there could be 6. So can you find the other ones? Well, the fact is, every single one of these is imaginary, which means not only is this a 0, but its conjugate is a 0. So that means if I is a 0, then so is its conjugate, which is negative I. If 3 minus 2i is a 0, then so is 3 plus 2i, its conjugate. If negative 2 plus I is a 0, then so is negative 2 minus I, its conjugate. So how many zeros do I now have? I have 6 distinct zeros. So again, just understanding that that theorem is very powerful and it can give me the extra zeros that I need to come up with, or once I have, in other words, once they've given me an imaginary 0, I automatically have another one, its conjugate, which is kind of nice. So the second example says that they want me to actually write the equation, and what they're telling me is that it is degree 5, and if it's degree 5, then that means I'm going to have an x to the 5th in there, presumably. And it's telling me that the zeros are, let's see, 1 multiplicity 3, 1 multiplicity 3, and then 1 plus I. 1 plus I. Didn't say multiplicity, so that means multiplicity 1. And they're telling me to let A equal 1 in this equation. A is the leading coefficient, so they're trying to make it nice on me. And they're saying the leading coefficient, which will have an x to the 5th in it, is going to be a 1x to the 5th. So leading coefficient is 1, so I don't have to worry about that. So here's the deal. Zeros, 1 multiplicity 3. So technically there is a 1 and then a 1 and then a 1. So there's 3 of the degree 5. And then 1 plus I, there's 4 of the degree 5. I need one more, right? Either that or they should have told me this was multiplicity 2. But guess what? This is imaginary, which means that so also 1 minus I is a 0. It's conjugate. Now I have them all. But now they want me to write the equation. So f of x is equal to, so if 1 is a 0 multiplicity 3, that means its factor is x minus 1, and it's there 3 times. So a power of 3. The factor of x minus 1 is there 3 times. It's repeated. The 0 would be 1 from that. So now how do I write these down? So the 0, if the 0 is 1, then the factor is x, and then the opposite of that 1. So the 0 is 1 plus I, so the factor is going to be x, and then the opposite of this, and there are 2 terms here. So you take the opposite of everything. So I'm going to write down minus 1 minus I. This is also a 0. So my factor would be x, the opposite of this, so minus 1 plus I. So in other words, this piece right here is coming from the opposite of 1 plus I. This piece right here is coming from the opposite of 1 minus I, just like this piece right here is coming from the opposite of 1. So that filters through and gives me negative 1 minus I. This filters through and gives me negative 1 plus I. The book takes it further, and here's where I wanted to comment on the homework. So they take that and they make you multiply it all out. Boy, that takes another 20 minutes of work, possibly with mistakes that you then have to go figure out where you made a mistake. I just don't think it's worth it. So as a result, this is fine to leave it in this form. It's in linear form, even though it's got the imaginary components to it, which is nice because then I know what the zeros are. So I'm saying you can leave it in this form, which leads me to number 19 and number 21. The acceptable answers in the book for these two homework problems are x minus 4 squared, x minus 3 minus 2i, x minus 3 plus 2i. And for number 21, an acceptable answer would be x minus 2, x plus I, x minus I, x minus 1 minus I, x minus 1 plus I. You don't need to multiply those out. Just leave them like that. And so I just wanted to give that to you so that you could check yourself. One other comment here. Because I didn't multiply this out, can I still tell that it's degree 5? Well, this would give me an x cubed times another x times another x. There's my x to the 5th. And the fact is when you multiply with conjugates, all those middle terms go away. So all the i's are going to go away in my final form. And you know what? Here's an extra credit for you. So this is Thursday, April 2nd. So I'm going to make this due tomorrow, Friday, April 3rd, at whatever your class time would normally be. So for my 145 class, you know what? Yeah, so for my 145 class on Friday, no later than 145, you want to do the extra credit on this, multiply this out and tell me what the final f of x looks like. And for my later class, which starts at 4:30, 4:30 tomorrow, Friday, get it to me no later than 4:30. After 4:30, I'm not going to look at it. Extra credit, multiply that out and tell me what the actual polynomial looks like. So there's another opportunity. So we have 2 more problems to do. Let's go take a look at number 3. So 3 says, find the other zeros if one zero is 3i. So let's see, I've got f of x equals, they've told me one of the zeros is 3i. Okay, so let's see. One of the zeros is 3i, so 0, I know 3i. And the fact that they told me 3i means I also know negative 3i is a 0 as well. So they've given me 2 zeros and they want me to get this whole thing factored, or, well actually, they want me to find the other zeros, which basically means I need to go factor things. So they're telling me these are zeros, which means if I synthetically divide, I should get a remainder of 0. So that's what I'm going to do. If the 0 is 3i, I'm going to synthetically divide with 3i, and then I'll see what it looks like all factored. So let's see, everything's in order here, and I happen to know that this is a little more difficult, so I'm going to give myself a little more room. This will probably be the thing you like least about this section. I'm going to get practice synthetically dividing with an imaginary 0. So, let's see, I've got 3. So I'm going to spread these out a little bit. 5, 25, 45, and negative 18. All in order. Okay. So I bring down the 3. I have to get a remainder of 0 because they've told me 3i is a 0. And if 3i is a 0, then the factor is x minus 3i, but I'll worry about that in a minute. I'm going to synthetically divide. So I have to take 3i times 3, and when I do that, I get 9i. And then I add those two, but I can't add those two because they're not like terms, so I need to write down 5 plus 9i here when I add them. Here's where it gets kind of tricky. So now I need to multiply, right? It's multiply, add, multiply, add. So now I need to take 3i times 5 plus 9i, which means I need to distribute it. So I need to take 3i times 5, and then I need to take 3i times 9i. Well, 3i times 5 gives me 15i. And 3i times 9i, so now you're going to remember way back when, gives you 27i squared, but I squared is -1. So this gives me not positive 27, but negative 27. So when I take 3i times 5 plus 9i, I get 15i plus 27i squared, which is negative 27. And now I'm going to add these. Well, the real parts I can add. The imaginary parts I can't. The real parts are going to give me -2. The imaginary part is going to give me 15i. Can you write 15i minus 2? Yes. I'm just trying to make it mathematically correct and do the real part first and the imaginary part second. So -2 plus 15i. Now I'm going to multiply again. So 3i times -2 is -6i. 3i times 15i is 45i squared, which turns into -45. So again, 3i times -2, -6i. 3i times 15i is 45i squared, which is -45. And I add. These are real parts. Oh, look, they go away, and I just get -6i here. So, oh, thank goodness. 3i times -6i is a -18i squared. But -18i squared turns into a positive 18, and I get, there it is, a remainder of 0. I know you didn't like that much. So what is this telling me? This is telling me that right now I have a factor of x minus 3i, or in other words, a 0 of 3i, and this is the depressed factor. Oh, what a mess. So the depressed factor has imaginary parts and real parts. That's the constant. That is multiplied with an x. This is multiplied with an x squared. This is multiplied with an x cubed. I don't even want to write that all down. I just want to keep, they just want me to find the zeros here, right? So I'm going to keep going with the depressed factor. So this guy right here, this is the depressed factor. We need to keep going. We need to keep going. Which means that I'm going to take him 3, 5 plus 9i, -2 plus 15i, and -6i, and I'm going to synthetically divide again. But then you say, well, with what? If 3i is a 0, then so is -3i, so I'm now going to do -3i, because that's my other 0. And in other words, what I'm setting up here is that f of x is equal to, if 3i is a factor, if 3i is a 0, then x minus 3i is the factor. If the 0 is -3i, then x plus 3i is the factor. And I just need to know what this final depressed factor is. So in other words, I synthetically divided with the 0 of 3i, and here was the new factor, which I didn't bother to write down because it's a mess. I'm going to take that depressed factor, and I'm now going to synthetically divide with -3i, because imaginary zeros come in conjugate pairs, so this would be my other factor for the -3i, and I'm hoping that this guy, the next depressed factor, will be much nicer to look at. So let's go try this. I bring down the 3. -3i times 3 is -9i. You should see this happening if you've done things right. I add those, the imaginary parts disappear, and I just get a 5. -3i times 5 is -15i. Look at that. Imaginary parts, when I add, disappear, and I'm left with a -2. -3i times -2 is a positive 6i. I add these two, the imaginary parts disappear, and there's my remainder of 0. This is now the depressed factor. In other words, here's a 0, here's a 0, which is what we said had to be the case, which means the factor for the 0 of 3i is x minus 3i, the factor for the 0 of -3i is x plus 3i, and here's what's left, which is constant x squared, which is 3x squared plus 5x minus 2. I'm almost done. Linear, linear, not quite linear yet. So can we factor this with normal linear methods? So I'm going to go try, this is the harder big X. 3 times -2 is -6. Add to 5. So a 6 and a -1 multiply, give me -6. Add to give me a 5. Either do grouping, rewrite and do grouping, or take the 3x, put it over each one and simplify. This simplifies into x and a 2. This one doesn't. So I believe my factoring is x minus 3i, x plus 3i, And this turns into x plus 2, 3x minus 1. So there it is, all linearly factored. And the question is what are the zeros? So the zeros are 3i, negative 3i. The 0 here would be negative 2, and the 0 here would be positive 1/3, all multiplicity 1. This was the ultimate answer that they wanted, but I had to get it factored to go figure those things out. And it was tricky because of the imaginary zeros as a result. So we have one more to do, just enough time here. So number 4 says, can you find the zeros and write in linear factored form? So pretty much what we just did on this one. This one just gave us a little more practice with the imaginary zeros. There it is. They want me to find the zeros and write it in linear factored form. So again, pretty much what I did here, I found zeros and I have it written in linear factored form. So can I do it with this one when they don't give me any hint as to where to start with the zeros? So I'm going to do the P's and the Q's to give myself a running start here, just because when I look at that, I'm not sure that I can see a nice way to factor it in terms of grouping, because I'd have an x plus a 13 left over there, and I just not sure. I mean, maybe I can manage it, but I'm going to go ahead and get some more practice with the P's and the Q's. So factors of 85. Oh boy, here we go. 1 and 85. Give myself a little bit of room here. 2 doesn't work because it's not even. 3 doesn't work, and here's why. You can let your calculator help you, but to see if something's divisible by 3, you add up the digits, and if that sum is divisible by 3, then the number will be divisible by 3. And 8 plus 5 is 13, and 13 is not divisible by 3, so then I know 3 won't go into it evenly. 4 won't go into it evenly if 2 didn't, and 2 didn't, so 4 is out. 5 does because it ends in 5, so 5 and, let's see, 1, 17. 6 won't go in if 2 and 3 didn't go in. 7 you just have to test and it does not go in evenly. 8 won't go in if 2 doesn't go in and 2 didn't go in, so I don't need to worry about 8. 9 doesn't work either for the same reason 3 didn't work. When I add 8 and 5 I get 13, and 13 is not divisible by 9, so 9 is like the 3 test. 10 won't go in because it doesn't end in a 0, and at that point if you square the number you're trying to divide by and you're beyond this number, you're done. So I gave myself way too much room here. So this is it. And then factors of 1 is just 1. These are my P's, these are my Q's. So possible plus or minus P over Q. So 1 over, luckily there's only 1 here, so plus or minus 1 over 1, 5 over 1, 17 over 1, simplified, 85 over 1. So there's 8 possibilities here. So which one do I want to start with? Well, either just start synthetically dividing with 1, or you can play the little game I do, which is put the 1 in there and see if it works, because if it does, then you'll be done quicker, maybe. So if I put 1 in there, that's 14. You know, that's not going to work. Maybe negative 1 would work. That would give me negative 1. This would stay positive. This would give me a negative 57. This would stay positive. Way too much positive. So 1 and negative 1, neither one of those work. So I don't have to bother to synthetically divide with them. I'm going to go to 5 next. And if 5 doesn't work, I'll go to negative 5. So let's see. I've got a 1, a 13, a 57, and an 85. They're in order. Nothing's missing. So bring down the 1. 5 times 1 is 5. Add, I get 18. 5 times 18 is 90. There's no way that's going to work. So that takes care of 5. I'm going to go try negative 5 now. So you can stop if you think it's not going in the right direction. Just don't quit too soon. So negative 5 times 1 is negative 5. This gives me 8. Negative 5 times 8 is negative 40. This gives me 17. Negative 5 times 17, that looks familiar. That gives me negative 85, which there it is, remainder is 0. So that means, so far what I have is f of x is equal to, if negative 5 is the 0, my factor is x plus 5. The depressed factor is right here, x squared plus 8x plus 17. So again, what were the directions here? To write it in linear factored form and tell me what the zeros are. So I've got 1 0 so far, and here it is. It's not linear yet though, right? This is not linear, but it's quadratic. I have ways to factor this. If I do the big X, this is the easy big X if it works. Multiply 17, add to 8. So that doesn't work, right? But it needs to be linear factored form, and I need to find the zeros. So here's the deal. Find the zeros first, and then write down the linear factored form. So I'm going to find the zeros. Well, the fact is that zeros are where y is 0, so that means x equal to negative 5, or negative 5 is a 0, or I have to go solve x squared plus 8x plus 17 equals 0. That's what I'm going to have to go do. So I'm going to go solve that. So I can't get it factored, so I'm going to do quadratic formula on it at this point. So x is equal to the opposite of b, so negative 8 plus or minus the square root of b squared, so 64, minus 4 times a, which is 1, times c, which is 17, all over 2 times a, which is 1, so 2 times 1 is 2. And now I'm going to go get this simplified. So let's see, x is equal to negative 8 plus or minus the square root of, so this says 64 minus 68. So what's 64 minus 68? Negative 4 all over 2. Do not cancel yet. You cannot cancel these two. You need to be able to pull something out of this to cancel, and you can't. The number there is a 1. Simplify this as much as you can before you try to cancel anything. So this is equal to negative 8 plus or minus, what is the square root of negative 4? We can actually simplify that. That is 2i over 2. Now you can factor out a 2 from both of those terms, negative 4 plus or minus I over 2, and you can cancel. So x is negative 4 plus or minus I. Those would be my two zeros. So what do I have here? I actually figured out my zeros first. So zeros are, I have a 0 of negative 5, multiplicity 1, right? I'll even write that down. Negative 5 multiplicity 1. And then I have 2 more from this guy. The 2 zeros, they're imaginary. So I have a negative 4 plus I. And I have, and so I'm not even going to write down multiplicity 1, because if we don't write it down, it means it's multiplicity 1. And then I also have negative 4, the conjugate, right? Remember, they come in conjugate pairs every time. So there's my zeros. That was one of the questions. And they want this linearly factored. So in other words, this is not my final answer for the factoring because that's not linear yet. So linear, in linear factored form, f of x, trying to give myself room here, is equal to, the 0 is negative 5, which means the factor is x plus 5. The 0, one of the zeros is negative 4 plus I, which means the factor is x, and then the opposite of that, so plus 4 minus I. And the other 0, and I didn't give myself enough room, but we'll try to fit it. The other 0 is negative 4 minus I, which means the factor is x, opposite of this, so plus 4 plus I. This is my answer for the linear factoring of it. So here's the zeros, and here it is linearly factored. In other words, this piece 4 minus I comes from the opposite of negative 4 plus I, and this piece, the plus 4 plus I, comes from the opposite of negative 4 minus I. So you just take the opposite of everything, just like the opposite of negative 5 is positive 5 for the factored form. So there it is linearly factored, and there it is with the zeros. And we have finished chapter 5. And I remembered to give you the 2 answers to the homework, and I also gave you that extra credit challenge. and there's a deadline on it, so be observant of deadlines and what they mean. Let's see, and other than that, have a great spring break. I will be emailing you over spring break at the very least, just to give you your quiz scores, tell you where you stand, and probably near the end of spring break, like that Sunday night or something, I will remind you of the rules for a test. So I think that's it. Again, stay healthy, have a great spring break, and I'll see you shortly.